Hi, this is Dr. Vikas Paul. In this session, we are going to study about strength of materials, which is also known as mechanics of materials. So, strength of materials deals with the maximum load of any member before it fails and how much time it takes for the member to fail and the deformation of the member due to the load. In engineering terms, the strength is represented as stress. The stress is defined as internal resistance per unit area afforded by the body. You can see in the figure there, P is the applied force, compression force is applied on a body, and Q is the resistance force by the internal force of the body, and A is the area. P is the applied force, Q is the resisting force, A is the area. So stress equal to internal resistance by area, that is Q by A. So we can also write stress equal to P by A, that is applied force by A, but within the elastic limit, because within the elastic limit P will be equal to Q. Strength is the maximum value of stress which the material can sustain. If the stress developed is greater than the strength, then the structure will fail. Load is a kind of force. It is a mechanical force. Forces can be classified as mechanical force, electromotive force, and gravitational force. The mechanical force is a force which needs a direct or physical contact, whereas the electromotive force or gravitational force does not need a direct or physical contact. Strength of material is a branch of mechanics. Mechanics is divided into three types again: engineering mechanics, strength of materials, and fluid mechanics. In engineering mechanics, we'll study regarding the rigid bodies, strength of materials, deformable bodies. Fluid mechanics is all about fluids. So mechanics is a branch of science which deals with the force and energy and their effects on different bodies. Engineering mechanics deals with the study of force and energy and their effects on rigid bodies, that is no deformation bodies. Strength of material deals with the force and energy and their effects on the deformable bodies. Fluid mechanics deals with the force and energy and their effects on the fluids, that is liquid and gases. So different cases in which force can be applied on the deformable bodies you can see here. So in the first case, tensile force P, and second force, compressive force, and the third case, couple force can be acted, couple force, and then bending force, and then shear force. In all these cases, force is common. But when the direction of force is changed, various effects are being observed. So, type of loads next. In the mechanics of the deformable bodies, the following types of loads are generally considered: dead loads, live loads, tensile loads, compressive loads, shearing load, etc. Dead loads means static in nature. Example, self weight of roof. Next, live load. It is fluctuating in nature or moving. Example, weight of the train moving on the bridge. Next, tensile load. The load which tends to increase the length of the material. Example, pulling of water from well. Next, compressive load. The load which tends to decrease the length of the material. Example, sponge. Next, shearing load. The load which tends to break the material. Example, scissors. Classification of materials: elastic materials, plastic materials, rigid materials, malleable materials, and brittle materials. Elastic material. It undergoes deformation when subjected to external loading such that the deformation disappears on the removal of the load. So example, rubber, balloons, etc. Plastic materials, which undergoes continuous deformation during the period of loading and the deformation is permanent. It doesn't regain its original dimensions on the removal of the loading. Example, aluminium. Next, rigid materials. It doesn't undergo any deformation when subjected to external load. Example, metal rod. Next, malleable materials. Materials' ability to the hammered out into thin sheets is called malleable. Gold, wood, lead, etc. Brittle materials. They exhibit relatively small extensions. Example, glass. Stress. Internal resistance offered by unit area of any material to an externally applied load is called as stress. So you can see in the figure there, P is applied force on a body and body is resisting. The resisting force is R. P is applied force, R is resistance, R equal to P within the elastic limit. Next, stress. Sigma. Stress is represented by sigma. Sigma equal to resistance divided by area, which is also equal to applied load divided by area of cross section, but within the elastic limit. So units of stress is force per area, therefore Newton per mm square. Types of stresses. Stresses are direct stress, indirect stress, and combined stress. Direct stress is again classified into normal stress and shear stress. Indirect stress is again classified into torsional stress and bending stress. Normal stress can be again classified into tensile stress and compressive stress. So direct stress. These are the stresses developed due to the force applied which is parallel or collinear to the axis of the component. So you can see in the figure there, direct stress It is collinear or parallel to the axis of the component. Indirect stress. These are the stresses developed due to the movement or torsion. So stresses developed due to the movement or torsion is known as indirect stress. Next, combined stress. It is a combination of direct and indirect stresses. Normal stress. These are the stresses developed due to the force applied perpendicular or normal to the surface of the object. You can see in the figure there. Next, shear stress. It is a stress induced in the body when subjected to two equal and opposite forces which are acting tangentially across the resisting section, as the result of which the body tends to shear off. The body tends to shear off across that section. So shear stress equal to resistance due to shear force or tangential force divided by area of cross section. You can see in the figure there. Tensile stress. The stress developed in a body which it is subjected to two equal and opposite pulls, as a result of which there is tendency to increase the length. It acts normal to the area and pulls on the area. Q equal to resisting force divided by area of cross section, that is pull force by A. So pull force you can see in the figure divided by area. Compressive stress. It is a stress developed in the body when it is subjected to two equal and opposite push, as a result of which the area decreases. So sigma equal to resisting force divided by area of cross section. You can see the figure there. Torsional stress. It is defined as the shear stress which acts on the transitional cross section that is caused by the twist. You can see in the figure there. Bending stress. If the normal stress when it is subject to a longer load at a particular point that causes the object bending, it becomes fatigant, that means weak. Strain. It is defined as when a body is subjected an external load, there is some change in the dimension body. The ratio of change in dimension of the body to the original dimension is known as strain. Strain is equal to change in dimension by original dimension. No units for strain. Strain can be divided as normal strain, shear strain, volumetric strain. Normal strain can be divided as lateral strain and longitudinal strain, and both these can be divided as tensile strain and compressive strain. So linear strain, that is normal strain. The ratio of change in dimension of the body due to the deforming force applied perpendicular to the surface of the original dimension of the body. So you can see the figure there. Longitudinal strain and a lateral strain. A P tension force is applied there. Longitudinal strain equal to increase in length by original length. Lateral strain is equal to decrease in length by original length. So in compressive strain, it is vice versa. Shear strain is the strain produced by shear stress shear stress. It is a measure of angle through which a body is deformed by applied force. You can see there the shear strain tan theta equal to delta L by L. Delta L is the change in length. Theta is the angle there. Theta equal to delta L by L. So volumetric strain. It is the change in volume of the body deformed when a force is applied to the original volume. Volumetric strain equal to change in volume by original volume, delta V by V1. V2 minus V1 divided by V1. Units of stress, sigma equal to F by A. In MK system, force, kilogram force, area, meter square or mm square. Sigma equal to kg F by m square when area is in meters square. Sigma equal to kg F by mm square when area is in mm square. In SI system, F is newtons, area m square, meter square, mm square. Sigma equal to n by m square when area is meter square. Sigma equal to n by mm square when area is in mm square. Conversion factor 1 Newton per meter square equal to 1 Newton per 100 centimeter whole square, which is equal to Newton per 10 power 4 centimeter square equal to 10 power minus 4 Newton per centimeter square. 1 Newton per meter square equal to 1 Newton per 1000 mm whole square equal to Newton by 10 power 6 mm square equal to 10 power minus 6 Newton per mm square. 1 Newton per meter square equal to 1 Pascal. The large quantity is represented as kilo means 10 cube, mega 10 power 6, giga 10 power 9, tera 10 power 12. The smaller quantities are represented by as milli 10 power minus 3, micro 10 power minus 4, nano 10 power minus 9, pico 10 power minus 12. Newton is a force acting on 1 kg of mass and produces an acceleration of 1 meter per second square. Acceleration 1 meter per second square. So force m equal to 1 kg. 1 Newton equal to kg meter by second square. 1 Newton per meter square equal to 10 power minus 6 Newton per mm square, which is equal to 10 power 6 Newton per meter square. 1 Newton per meter square equal to 1 mega Newton per meter square. 1 mega Pascal equal to 10 power 6 Pascal. Here 1 Newton equal to kg meter per second square. 1 Newton per mm square equal to 10 power minus 6 Newton per meter square. 10 power minus 6 means micro. Therefore, 1 Newton per mm square equal to 1 micro Newton per meter square. 1 Newton by Newton per mm square equal to 1 micro Pascal.